says that I cannot hear you. So can you?
We can hear you now. We couldn't in the first 5 minutes.
Oh, you couldn't hear me.
No.
Okay, so I'm going to go start at the beginning. How about that?
Sounds good.
All right. What I said is, oh, somebody asked me, what are the steps that I've taken to reach to this point? So it took me about 2-3 minutes to talk about those things, so don't worry about it right now. Now, what I said is that, where are the critical areas in this part? Can somebody tell me? If you didn't hear me, then you don't know what I said. So can you tell me where the critical areas are? I'm sorry, where is that? Okay. Yes. Okay. So I understand. You have the right answer, but let me repeat what I said. A lot of people will look at this and say, oh, it's the place where the stresses are the largest. Okay? Large places where you have huge stresses. That is strictly not true. Because if you take a block of aluminum or steel and dump it in the ocean, and it went to the bottom of the ocean, the deepest place that you can find on Earth, of course it gets squished, right? It gets squished, and you bring it up, then it goes back to its original shape. It does not deform permanently, because to us, failure means, critical means places where it deformed permanently. Because hydrostatic stress, large stresses, if it's hydrostatic, has no bearing on failure. The places which are critical are where colors change very rapidly, stresses change very rapidly. That you can see in this particular problem, it's either here or at the root. Can you hear me? Can you hear me now? Yes? Can you hear me, or is it still not audible? Okay, very good, very good. Okay, now if you say, well, which one? Use your common sense, use the stuff that they taught you in stress analysis or deformable bodies. You know that either here or there, depending on where the relative length of these pieces are. If this horizontal piece is very fat and short, then the biggest stress is going to be down here. On the other hand, if this horizontal piece is very long or thin, that's where it's going to deflect most, and that's where the bending stress is going to be critical. Okay? So, anyway, that's what I said, and you didn't hear me the first time. Now, what I want to do is I want to change my load. I want to change my load and repeat this problem. Okay? So the first thing is I saved already everything that I've done. My part and analysis up to this point is all saved. I hope you agree with me. Now, I'm going to close this. I don't need it. I'm going to go back to the original part. This was the original part, and save it under a different name. So you go to File, Save Management. This is the original, this is what's open, Save As. Save As. In that folder, the original one was part 1. It's a bad idea to call this thing part 1. I'm going to call it part 1. How about with symmetry? How about that? With symmetry. It's very common. People are careless. They overwrite the stuff that they have done. And when they go and try to submit it, it's all gone with the new stuff that they have done. Okay? In the first place, it's a bad idea to do this thing within this directory. But if you insist to do it in this folder, okay, change the name. Don't use part 1 because it's going to overwrite that. Part 1 with symmetry. Okay. So in that folder, I have 2 parts. The original part, which was called part 1, and the second part that I just gave you that name. You know, the thing is that it's a good practice to change the name up here so that you know what you're dealing with. Okay, I didn't do that when it gave me the default part name. I took it. I should have changed it there so that it was not called part one. It was called something else. Now, I want to repeat this problem, except that the load, I am not going to put it in the direction X. I want to put it in the direction Y. In the direction Y. 2,000 pounds in the direction Y. Okay. All right. So the part is right there. It's saved. Now think about it. If the bottom is fixed, if the bottom is fixed, if the bottom is fixed, and you apply a load in the direction Y, it's coming towards you, do you agree the stuff on half of this is the same as the stuff on the other half? If you cut this thing in the middle, do you agree the deformation is going to be the same on both sides? Yes or no? Yes. If it was applied in the direction that I showed you initially, there won't be any symmetry. If it's, remember, this thing bends, okay? There is no symmetry. But if the load is coming towards you or away from you, perpendicular to that face, then I don't have to do both of these. I need to do only half of it. So that being the case, I'm going to reduce the model by taking half of this, okay? So let me go to split, surface-based feature, split. CATIA calls it split. It doesn't call it cut. And I'm going to split it with a plane that puts this thing in, makes it in two halves. This is very convenient because I already have a plane like that. It is the YZ plane. YZ plane. And it says, okay, do you want to keep the left side or right side? It doesn't matter to me. I'll just keep this. Okay. I'll save it. When I save, of course, it's under the second name because, you know, that's how I saved it. That's what I did a minute ago. Now, symmetry is a big chunk of your mark on the midterm because it makes you think, okay? So don't be surprised if a problem that has, in this problem, for example, if it has 10 points, just hypothetically, on the midterm, if it has 10 points, 3 of them, something to that range, would be identifying symmetry. Okay? Don't be surprised. Now, as far as making the model, it's done. Now we're going to go, the person who asked me about what are the steps that you did, here, just follow me. Remember, material is already applied there because it came from the other part that I saved it under a different name. So you go to Start, Generative Structure Analysis. In your case, because you have not customized it like that, you go to Analysis and Simulation, Generative Structure Analysis. CATIA sees a solid object, immediately it meshes it. There, it meshed half of this. Static problem. If you want to see your mesh, put the cursor on this line, right click, mesh visualization. There we are. Okay, there we are. To do the rest of the problem, you have to either delete the mesh or deactivate it. It will not allow you to put forces and moments and restraints on this. This is a mesh. It's totally useless. Right click, deactivate. And if you don't like this rendering, change it to some other kind of shading, right there. Okay, and you know how to refine the mesh if you're asked to do it in a specific area. I'm not going to do that, okay? I already showed you how to do it. You go to the place where the model manager is, the traffic light, second toolbar, local mesh size, and you go and pick the thing and do it. Well, I'll keep it like this. You're going to do that on the first assignment anyway, so, and on the test. Okay, now the bottom is clamped. The bottom is clamped. So there's the clamp. There we are, clamp. There's the clamp. There we are. Okay. And I have to apply a force here, coming towards you at 2,000 pounds. Okay? Can somebody help me? This was the force, right? This was the force. Distributed force. Distributed force. In the direction, in my case, y, correct? Is that right? Look at your screen. It's coming towards you, direction y. So not x, y, 2,000 pounds. And the support is right there. This is the support, right? It's asking for the support. Where are you applying this force? Well, it's on that face. Say okay. You know what? If that problem had 10 marks, you'll probably lose 2 marks for this. Can you tell me why? Well, if you're pushing it into the screen, yes, you're right. But if you're pushing it away towards you, you're of course pushing it like this, right? So in one case you're pushing it this way, in the other case that way. Let's say that this was actually the way I wanted to do that. You still use your 2 marks. What's the issue? I'm sorry, say that again. Yes, yes. Because that 2,000 pounds in on that entire face. You're taking half of that face. So you divide it by 2. That's very easy to fix these. You go to the screen or you go to the tree, double click on it, and make this thing 1,000. Okay, good. Now let me ask you a question. Suppose I said 200 psi. I'm applying 200 psi on that face. What value would I use for the pressure? Yes, pressure is pressure. Doesn't matter how you, if pressure is on that surface per unit area. So if this was psi, don't divide it by 2. If it's the force, you have to divide it by 2. Excellent. So before I run it, let me go and save this. Save the analysis, because as soon as we jumped in there, we created an analysis file. So you go to File, Save Management. This is the analysis. Save as. I don't want to call it this. I want to call it problem 1 with symmetry, right? Symmetry. With symmetry. With symmetry. Okay. So that it doesn't mess up the guy that's already up there. I don't want to destroy this. This was the original problem. Okay. Should I run it? Yes? Can you help me? Is there something else that I have to do? Well, I mean, you can run it. There's no problem. Just run it and see what happens. And you can look at the deformation. Deformation is this, no numbers. This is deformation. You click on it, it shows deformation. And let's look at it from a view, front view. Okay, so front view is, I guess, this one. This is side view. Whoops. I guess side view right there. Okay, and I can animate it. Okay, that looks good. That looks good. Now I want somebody to criticize me because you don't want to lose your 2 marks on the final exam. Oh, not final, midterm. Midterm exam. What is wrong with this picture? It looks good. I can plot the stresses, everything looks reasonable, etc. But there's a serious problem. What do you say, guys? Gals? Oh no, I did put the force. I put 200. I put 1,000, right? I did put 1,000 pounds. I did put it. That's why it's actually coming towards you. There is a force there. Here, let me turn it around. You can see that there is a force, right there, right there. You can see that. What else? Okay. No, we can do that. There's no problem. Here's just, you want to plot the one meter stress? I'll plot it for you right there. Well, you get stuff. You get stuff. So let me change this thing to material shading. Sure, there is. Where's material shading? I'm going to move this thing up there so that material shading. There's a stress. There's a stress. I mean, you can rotate it, put it in this view. Let me ask you this. Whoever told me initially that there is a plane of symmetry here, I said, use your common sense. Look at this thing from the front. Let me see now. Let me bring this thing, the same view, but the part. Let me put it in that view. It was the side view, right? Side view. Okay. You looked at that and you told me that the stuff on the left and the stuff on the right are the same, right? They behave the same way. And I agree with you, correct. So if you are a point on that face, on that surface that I introduced here by cut, see that? I introduced this surface artificially. If I look at a point on that surface, can it go to the left or to the right? Need help? Help me. If I look at a point on that face, can it go in the direction X, either to the left or to the right? It shouldn't. And that's what we call a roller, right? We call it a roller. The points on that face must be, plane of symmetry must be on a roller. When you look at the analysis that I did for you here, if you looked at the deformation, look, it moved. It moved to the left. It moved to the left. This top piece moved to the left. Even here they have moved to the left. I can see it very well because it has moved very little. So just cutting the piece into two, which is good. It gives you some marks. Just cutting the force into two, that's good. That gives you your mark. Is not good enough to get the full mark because you have to put that face that you introduce on a roller so that it doesn't move to the left or to the right. That's what the plane of symmetry means. So CATIA does not have something called roller. It has something called surface slider. When you look at it, though, it looks like a roller. Okay, so let me deactivate this. When these things are on the screen, you can't apply anything. So you turn this thing a little bit. Surface slider. See that? Surface slider on that face. See that? If you look at it from close, it looks like a roller icon. See that? Looks like roller. Okay. And say okay. And save it. The reason it's a good idea to save before running, because if you accidentally, the system crashed, or you put such a fine mesh there that it takes forever to run, you're not going to finish your test on time, then at least you can kill the job, kill CATIA, and then go and get your last saved result. Okay? Now let's run it. While this is running, I have to repeat this lecture 3 more times. Don't worry about this warning message. Don't worry about it. You'll get used to it. It's a good idea to read these things and sometimes question them, but not right now. First lecture, basically. Good. So now let's look at, for example, your von Mises stress. View from the side. Look, there is no going to the left or to the right. You can animate it, by the way. There is no going to the left or to the right. That gives you full mark. Otherwise, you lose too much because of the surface slider. Because it's very common. People, they see it. They cut it into 2 pieces. They see the force must be half of that. That's good. But they forget about this, and you can see that it's wrong, basically. Okay? All right, guys. Any questions about this? Okay. Now, before I kill this, let me save it so that the last thing that I have done is saved. And now when it comes to uploading your work, either for the homework or for the test, what two files you have to send us? You have to send us the part file and the analysis file. I'm going to kill this one too. Okay, so let me see, where is my desktop? Okay, so look, this schedule is so screwed up that I have to make this so I won't forget. Here's your lecture. Where is this guy? Where is that folder that I made? Right, May 10th. Remember, I made two parts, one with symmetry, one without symmetry, and two analysis, one with symmetry and the other with. These are the analysis file. These are the part file. Okay. So you select example part with symmetry and analysis with symmetry and submit it. Okay. Any questions?
Sorry, sir. Just to clarify, we don't need the cat analysis results and analysis computations files.
Okay. Yeah, I will do that. But the other fellow was asking. Can you say that? The first fellow was asking me about you don't need to what? Say that again.
So I think you have two different classes open right now because we can't hear the other class, but do we need the analysis results and the analysis computations files?
Okay, hang in there. No, just 1 second. I want to make sure I understand what you're saying. You have two different classes. What two different classes?
Yeah, the people who were in the section from before, we
Yes.
can't hear them talk. They never changed classrooms.
Well, okay. Listen. Oh, really? Wait a
Yeah, so
minute. This
there's
lab. Oh, let me ask you this. Let me ask you this question. Are you registered in section 2 of the course?
yes.
Okay. If you're registered in section 2 of the course, whether you're in lab section 53 or 54, you should be able to hear what I'm saying.
No, what I'm saying is, you know how you created a first 50-minute session and then a second 50-minute session?
Yes?
There's some people in the first 50-minute session first still, and we can't hear them. That's why there's confusion.
Uh, were you in the first 50 minutes too? Yourself, were you in the first 50 minutes?
I'm talking from the second 50 minutes, but I was in the first 50 as well. I just left it.
Okay, so you're okay then. You can hear me. Is there, well, let me see now. Is there someone who was in the first 50 minutes and now they cannot hear me?
No,
Or
I think we can
actually,
all hear you. We just can't hear anyone
they,
else.
okay, I'm sorry, I don't know. I have to find out what the issue is because I don't know.
Yeah, I
Now,
don't think it's important. I was just asking if we need the analysis results and analysis computations
okay,
files.
yeah, all right, right. Here's the situation. Uh, what we need for marking is your part file and analysis file. That's all. We don't need two extra files that may have been created for you. One of them is called computation, the other one is temporary, something like that. Am I correct? There's two other files that you were created on your, probably in your folder. We don't
Yes.
need those because what we do when we get your analysis and part file, we're going to run it. We're going to run it. So those are temporary files that are created that you don't have to give it to us. Just the analysis and the part. Are we good?
Yes, thank you.
Okay, all right. Now, if you say, what the heck are those other two things are for? Well, let me put it this way. If you were doing this thing for a living and you spent 5 hours of CPU time to run this problem, and you decided that, okay, I'm going to come back on tomorrow and look at the results, show it to my supervisor, and you had not saved those computation and the temporary file, then you have to run it again another 5 hours. On the other hand, if you save those for yourself, then tomorrow when you come back, you don't have to run it because those two results files are there. We don't need it though. Our problems are all Mickey Mouse problems. We just click the compute, it will run for us in no time. Okay, now let me go to my second problem. Second problem, let's see now, where is it? Okay, so we have an I-beam like that, and one end of it is clamped, and we let it sag under its own weight. Sag under its own weight. Okay? So we want to see what are the stresses, what are the deflection, etc. First of all, notice that I'm saying I-beam 10 inches long. Well, imagine that you have an I-beam that's 10 inches long, something, something that you use in construction, 10 inches long, and you somehow clamp the other edge by welding it to some other piece. How much do you think it's going to deflect? Very little. Do you agree? Okay. So this is an academic exercise. I want to show you how do you bring the weight of the object under the force. There is no force here. There is no applied force. You're not applying any force. The weight comes from gravity. I want to show you how you do that. Now, first I will do it the way it's done in the book. And if you go to my website, I mean, those links that you have, you see it done both ways, with symmetry and without symmetry. First, I'm going to do it without symmetry. And I don't want to spend time on making these dimensions. So I will make up something that's, something like an I-beam type thing, and then 10 inches long, okay? This problem is a disaster if you solve it the way I'm going to show you. But right now, that's all we know. All we know is solid elements. Just wait for 2 more weeks, 3 more weeks. I'll show you shell elements, and we're going to do that later on. Okay, so let me go, Katia. Start a part file. Remember, I left this name as part 1, and that's why I'll call it part without symmetry. How about that? Part, because it's easier to me to keep track of these things. Part without symmetry. Part without sim. How about that? Just like it's done in the book. Okay, save it right away. File, save management, save as, desktop. Where is it? Desktop, new folder, May 10, lab 53, underscore problem 2. Okay. So it's going to go in there. Say okay. Say okay. Let's make it. On a convenient plane, on that vertical plane, I will sketch something that looks like an I-beam cross section. So be patient with me because I want to use something that is used very frequently. So I'm going to draw something that is ridiculous, doesn't look like what I want, and I'm going to show you how to fix it. Okay, this is my I-beam cross section. Let's do a cleanup here. First of all, I want this guy and that guy to be aligned. So this line, control that line, and you go to constrain using dialog box here, and you say coincident. Okay. This line, control that line. I think they are on the same plane, but so we make it coincident. Okay, good. This line, control that line. We want to make them parallel. Parallel. Okay, very good. This line and that line and the middle axis, I want to make them symmetric. This line and that line and middle axis to be symmetric. This line and that line and the middle axis to be symmetric. Okay, top line, bottom line, middle axis to be symmetric. And so let's do this one. This line, control that line, control middle axis to be symmetric. Oh, God. So let me see. Okay, I think these are already symmetric. These are, no, maybe not. And let's proceed. That line, control this line to be coincident. Okay. And this line and that line to be coincident. Okay. Now, these are not symmetric, but let's see now. I don't know why it was bombing out on me. Maybe these dimensions, let's take these dimensions out. Yeah, let's take these dimensions out. I didn't mean to put dimensions there. This line, control that line, middle axis to be symmetric. This one should work. Yeah. And finally, that line, control this line, control middle axis to be symmetric. Now you drag this thing any way you want. It's going to stay the way you want it. Look, I don't care how you do it. I want to show you this is a very valuable tool. That's all. That's what I want to show you. And just so that you have a rough idea, let's put the dimension on one of these at least to find out how big these things are. So this thing is 6 inches, and I-beam 6 inches. Probably that's okay. Yeah, 6 inches. That's okay. Is there any question? Make this I-beam the way you want it, matching the dimensions that you would give it. That's all. Okay, exit. The only thing is that 6 inches. Isn't that too big? Maybe 6 inches is, because I'm padding this thing, but because I'm padding it by 10 inches, maybe I should change this thing to, I don't know, maybe 3 inches. Yeah, okay, that's fine. And let me also move. Okay, good. Because I'm padding it by 10 inches. Okay, so exit, not exit, pad it. 10 inches. Good. All right. So apply material to it, made out of steel, metal, steel, on that face, on that part. There we are. Save it. Now we're going to go to generative structure analysis. Analysis and simulation. Generative structure analysis. CATIA immediately measures that for you. So if you change the rendering so you can see it better, right there. You want to see your mesh? Put the cursor there, right click, mesh visualization. Okay. Now, this is not too bad, but generally speaking, I-beams, the flange is a lot thinner than what you see here. And the web is a lot thinner than what you see. You don't see I-beams of, like this, okay? Or at least used in what I mean is used in structures. Now, look, if this was thin as opposed to what it is now, you would have only one element through the thickness. The moral of the story is that because of the dimension of this, think about it as a pop can. A pop can, it has a thickness, but the thickness is a lot smaller than the other side's dimensions of the part. So you do not model those things with solid elements. But this is the only thing we know how to do right now. So right click, activate, deactivate. Shall I save it? File, save management. This is the analysis. Save as. In that folder, let's give it a name. May 10, Lab 53, no symmetry. How about that? No symmetry. So that I can identify what these things are. You say, okay. All right. The end is clamped. This end is clamped. Clamp that end. So what it does, it puts it on the entire thing, but for demonstration purposes, it probably puts it on the centroid. Now, I want to apply my load, right? Load. Okay. What do you suggest? How much force should I put up there? And where should I put it? Am I applying a force here, for example, of some magnitude, or what do you say? What is the force that's acting on this part? Or how would you calculate it? Yes, yes, you're absolutely right. I have no clue where the geometric center is, and it can be found, but there is a way to say, okay, why don't you give this object an acceleration? See that? Under the load, you see a globe here, and there is a downward arrow that reminds you of Apple Newton. Remember that? You click on it, it says, okay, what is the thing that you want to specify gravity acting on it? Well, gravity is a body load, body force. It doesn't matter what you pick. It picks the whole thing. That's why you don't have to go find the weight. It'll do it for you. And it says, okay, this gravity, in what direction is it acting? Well, it's acting in direction Z, negative Z direction. If you don't know what it is, I'm sure you know well, minus 9.81. How about that? Is that good enough? You remember from physics, 9.8? Or no, yeah, there we are. It does it for you. You don't have to find the geometric center. You don't have to find the weight. In fact, if you do it like that, you're going to get different results. This is different. This is different. Okay, so save everything and run it. Compute. Horrible mesh. Look at the deflection. Oh yeah, that looks good. at least it doesn't twist. So these things are good for supervisors that they want to look at things and see whether, oh, no, actually engineer. You want to have a first impression that if this was going to the right, you suppose there's something wrong here. Okay, good. Now, if you look at the stresses, it's going to be extremely small. Imagine this is an I-beam. This was, I don't know, it's 1 inch. Oh, how much weight does it have? 21 psi. That is nothing. That is nothing. So look at the material shading. Biggest stress at the wall. Okay, I took my strength of material. I know what it deformable bodies. I know where the biggest stress is at the support. 21 psi. That's nothing. You know what the atmospheric pressure is? Atmospheric pressure. You remember that, right? Don't you watch the news? Yep. Good. Good. Somebody's going to answer. Yeah, 14 psi. So basically, we have air. So you're right. If you look at the deflection, it's nothing. Deflection, magnitude, size, something 10 to the minus 6 inches. So we know how to do it. It's just it doesn't make sense. Because why would you want to know the stress in an I-beam, 10 inches long, 1 inch thick? Nothing. Now, why is this thing useful? If this was your car antenna, you know the antennas that come out of the telescopic antennas that you take out, and you sit and you accelerate, it's like gravity, but it's not really gravity acceleration. Gravity is acceleration. So if you want to solve like that, a problem like that, or if this was an object which was sitting on if your car was going at 10G, you're going to become unconscious, of course. 10G, you can do that. It'll bend, but of course it's not gravity. That's what you use this thing for, if needed. Now, the other thing is, what if I want to use symmetry? Let's do that. Let's do it. So let me save everything. It's going to take only 3 minutes at most. Kill that. This guy, I want to save it under a different part name with symmetry, okay? So file, save management in the same folder. But I don't want to call it without symmetry. I want to call it with symmetry so that it doesn't screw up the other part. Okay. Now I take half of this, right? Remember the view? Don't take a quarter of it. Because if you take a quarter of it, if you was pulling this or pushing into it, yes, quarter would be plane of symmetry. But this is bending. So there is only one plane of symmetry, which is vertical. So cut it with this plane. And because I made it symmetric in the first place, it looks okay. If this was not made the way I made it, then you have to go and create a plane exactly right in the middle and then cut it with that. We're almost done. Save this. Go to the analysis, generative structure analysis, static, save it, file, save management. We already had something there. We're going to give it a different name, we're going to call it with symmetry. With symmetry. Say okay. Left end is clamped. Apply gravity load on it. Anything that I did before is still valid, unless you erase it. On that object, doesn't matter what you, even if you pick the corner, because these are body forces. It's entirely on the entire object. Help me with the last 2 marks of a 10-point scheme, test that you wrote. What is the last thing? You out of 10, you're going to lose 2 for sure, something like that for this problem. If you run it like this, help. Yes. Surface slider on that face. Okay. Save it and run it. Don't worry about this. Take the time, breathe it once, and ask me in the office hour or something like that. And if you look at the view from the, I don't know, side, okay, good. This is going to go up and down. It's not going to go to the side. Here's the stress. You can animate it. Okay. Now, last thing I want to show you is that, look, there is an icon here. Look, there's an icon here, amplification factor. You click on it. It took that amplification factor because the deflection was so small that it had to magnify everything by a factor, gigantic factor. It'll do it for you. You can change that. Would you like to make it 1,000? It's a big number. Change it? I can't remember. Well, let's make it default. Let's make it 1. Wait a minute. What happened here? Hang in there. Something is screwed up here. This is my, okay, very good. Okay, so amplification. This is the default, okay. Okay. Okay, let me put it, let me magnify it more. 10. I know what happened. Let me make it, magnify it more. You see, this internally changes it so you can see on the screen. If you go default and fit, there you are. This is under your control. For example, you can make it 8 times. 10 to the 8. There. Okay, so let's make it 6. There. Okay. Don't let this thing distract you. You have a control over this. CATIA will choose an optimum so that it fits on the screen. Okay. So there we are. But this is under your control. Make this thing 6. And that's what you're going to see. All right, folks, this is the end. So I'll hang around for another. Listen, as far as recording is concerned, this is the end. And I'm going to save this thing, but I'll hang around. And if there are any questions, please feel free to ask. So let me save this. Cancel that. Okay, sometimes this happens. If it happens, just click on something else. I don't know. It'll kill that window for you. Okay, cancel. All right, good. So save it. You know what? I'm not going to stop it in case there are any questions. Are there any questions about this? Yes, you can create a video file. Let me look into those things, and I'll let you know next time. The answer is yes. But believe me, all the stuff on the YouTube. I don't remember. I have a segment on that business of saving these things, but I'm not the only person who's doing this. However, there are not that many people doing FEA in CATIA. And do you know why? Because CATIA is an excellent CAD package. Excellent. State of the art. But what they did back in about 20 years ago, they put a finite element solver, a limited finite element solver, which is called Elfini. Elfini is a French code. It's called element fini, finite element, element fini. And it does basic stuff for you, not advanced stuff. For example, you cannot do yielding, you cannot do plastic deformation, which is the same as yielding. You cannot do blowing of a balloon. Blowing of a balloon. The strains are infinitesimal in the formulation of CATIA. Material must be linear. You cannot do nonlinear material properties, etc. For the purpose of teaching a first timer, this is good. If you're a designer in industry who are not going to get into these complicated analysis, this is excellent. But because the work, the analysis is usually not done by designers, what they do is that the designer makes a part, a complicated part, and then they ship it to the engineering department. And somebody who has taken an advanced course, somebody who knows other software, if needed, is going to use those packages. So you're not going to see a lot of references to finite elements in CATIA. But you have to live with it. First time, that's okay. We'll do it the first time. Okay, anything else? Do you know why we are using it? You know why we are using it? Because the suppliers here or employer of our students, many of them asked for it. So this is we were using other things, but maybe 15 years ago, 16 years ago, Chrysler said that we want this because at that time it was Chrysler, Benz, Daimler, Chrysler. They said we want a European code. Okay, we got the European code. Any questions? Any questions? Are we good? Okay, folks. See you on. Is it tomorrow? Yeah, see you tomorrow. Have fun. Yes. Oh, I will do that right now. I will do that. Thank you. Thank you. See you tomorrow.